Hello, all. I'm Sandan Kumar from AML department. Today we'll be discussing about the SR flip-flop using case, which is set reset flip-flop. So basically, we have to implement the S flip-flop using verilog, and we have to validate their functionality using the truth tables. So here we can see the circuit diagram of the SR flip-flop. Basically, we have set, reset, and the clock, and the NAND gates respectively, which obtain the Q and Q bar. So basically, this is the truth table of SR flip-flops here. So our aim is to implement the SR flip-flop in the quartus using verilog programming. So basically, let's begin with the program here. So we are declaring the module experiment, which is the name of my project. And then we have the inputs S or clock and reset. As we can see here in the plot diagram, we have the inputs as S or clock and reset. So and then we will begin with the always positive edge, which will be the basic condition of the SR flip-flop, which will be working on the positive edge of the clock. And then we'll begin the condition. So when not the reset is not equal to 0, we'll be declaring Q less than or equal to 0, or else we'll be making the case as set and reset. So as we can see in the truth table here, when it is 0, 0, it's basically of no change. When it is 0 or 1 or 0, the states are being complemented. Sorry, the bits are being complemented. So same way we are going to modify this. So whenever it's q less or equal to q, no change. And then we'll be making the remaining logic for reset and set for the other cases. And we'll be ending the case statement and then the begin and then always finally we'll be ending the module. So press Ctrl S for saving the experiment. Click the run button. So it's being executed. So we have executed the program without any errors. So for the circuit diagram, we have to view the RTL view, which will be found in the netlist view, so RTL viewer. So we have got the logic diagram here. We have the reset and set, and then the 3 to 2 mux, which is being directed to the Q and Q bar, which are the outputs, and we have the basic clock and the reset. So in this way, we can obtain the RTL view of the given SR flip-flop. For the waveform, we have to create a new waveform file. Basically, we have to edit the settings here. We'll be setting the end time to 200 ns. And then we have to insert the nodes, which will be directly directed by the program. So experiment is the program. We'll be listing and we'll be transferring the nodes here. So we can see here the inputs are clock and then R S. So basically the outputs are Q and Q bar. So for S R reset, we have to give the values as 0, 1 and etc. So we can do this by giving them as 0, 1, 0, this is 1, 0, 1 and etc. It goes on with the respective truth table values. So basically this is how we can arrange the university waveform, and finally we can run the stimulation using the run functional stimulation. So we'll be getting the outputs of the Q and Q bar. So this is how we can create the simulation waveform file and the netlist waveform RTL file using the Verilog programming. So in this way, we can implement SR flip-flops using the Verilog programming, and we can validate the functionality using the logic gates and etc. So thank you.